Okay, so you can see I've got the periodic table here in front of me instead of a calculator. So we're going to be really living and breathing by this periodic table here. Okay, so recall. So last time I described that because of all of this electron interference and electron, what we'll later call shielding, the levels split. Okay, so 2s and 2p are only the same for hydrogen, but not for anything else. 2s and 2p levels split for any other electron. Okay, and so the order of levels gets really complicated. And as we're also going to see, there are exceptions, which I'm not going to worry too much about the exceptions. There are a few exceptions that I do want you to know. Okay. But we don't have to memorize this as long as we can read it off the periodic table, right? So starting at hydrogen and helium, that's 1s. And then the next level, lithium and beryllium, 2s. And then if I keep going across, boron through neon is 2p. Okay, and then moving along, 3s. And then 3p. And then 4s. And then now 3d, 4p. 5s, 4d, 5p, 5s, and then after 5s, 4f. And then now after 4f, 3, 4, 5d, then 6p, then 6s, then 5f, and then finally 3, 4, 5, then 6d. Okay, so the slide that you want to study from to get those orders is this slide right here. Okay, that's giving me those correct orders. If I start from the top left corner, left to right, top to bottom. So left to right and then move down one, then left to right and then move down one, then left to right. Okay, so let's go through it. We're going to go through many examples here. Okay, so let's start with hydrogen. And so what I'm also going to do is introduce something called electron configuration, which is a type of notation that we use to summarize this diagram. Okay, so hydrogen on the periodic table, there it is. It only has one single electron. Okay, and I put that electron into this orbital by drawing an arrow pointing up. I could have drawn an arrow pointing down. Remember, that's plus 1/2, minus 1/2. We don't know which one it is, okay? But because there's only one in there, that's the only one that I put in. And then look, based on this, my electron configuration, I write it as 1s1. So 1s1 is the address of hydrogen on the periodic table, okay? 1s1, there it is, all right? So what about helium? Well, helium's next, right? One more over, okay? So helium has 2 electrons. So how do I populate them in this diagram? Well, I go 1, 2, and now that makes an electron pair. This is why helium is a noble gas, because as it turns out, paired up electrons are really stable. We will see that's what the noble gases have in common. They have all paired up electrons, okay? And so now the electron configuration for helium would be 1s2. The 2 means 2 electrons in the 1s orbital. This is helium's address, 1s2, okay? And so I'm just going to keep going through examples, and all we do is just keep populating them based off the Aufbau principle. Electrons are added one at a time to each successive orbital in order of energy, okay? So we did hydrogen 1s1, we did helium 1s2. So as you can see, what's going to come next, lithium, 3 electrons, 1, 2, 3, okay? And so I do it by saying 1, 2, 3. We only pair up the electrons if we have to. Because after all, they are electrons, they're negatively charged. They do want to repel each other somewhat, okay? So now this address or this electron configuration becomes 1s2, 2s1. Okay? There's another shortcut that I could also say, all right? And because, for example, I know helium is 1s2, when we write helium in a block like that, that's the same thing as saying 1s2. So I could write lithium's electron configuration as helium bracket 2s1. Okay? Either or works. So when you say the complete electron configuration, that usually means this, 1s2, 2s1. But we can use it's called the noble gas shorthand notation. And we can replace a noble gas configuration with that noble gas symbol. As you can see, for helium, it doesn't really do much for us because it's just as easy to write 1s2 as it is to write helium. But as we get into the heavier elements, like iron or rubidium or something like that, this noble gas configuration becomes a lot more useful, as you will see. Okay. So now what about beryllium? 4 electrons. 1, 2, 3, 4. There's beryllium. Okay. So I'm going to go 1, 2, 3, and now where do I put it? Well, you notice that beryllium is still in this 2s block, right? So it gets paired up in the 2s. And I could write this configuration as 1s2, 2s2, or I could write this configuration as helium 2s2. Okay? That works. Let's keep going. Okay? And as you can see now, what I've done instead of going through all of those one by one, which I could, right? If I were to go to boron next, then boron is going to have a p electron. Okay? So here I'm showing the diagram for you just slightly different, only showing you the 1s, 2s, and 2p. Okay? So, but now as you can see what happens, right? Lithium and beryllium, we did those examples, 1s2, 2s2, which I could also write as helium 2s2. But now look what happens with boron. Boron, we get one extra electron, so we place it in that first 2p block. Okay? And now that becomes 1s2, 2s2, 2p1. Or I could write it as helium 2s2, 2p1. But now look what happens with carbon. Okay? So I'm adding one more electron, but I don't pair it up because there's open orbitals. And if there are open orbitals, those electrons will spread in. Much like how you all are in the lecture hall, if there's an open seat, you will take it, right? I know this. I've been teaching college for 10 years now. If there's a seat next to a person, but then there's also an open seat, you're going to take the open seat. I know this. You're not going to take the seat next to the person unless you really like that person and you're trying to date them or something. So the electrons will fill into the open spots, right? So carbon becomes 1s2, 2s2, 2p2, or helium 2s2, 2p2. Okay? And now you can see we go one at a time. So nitrogen becomes 2p3. Oxygen, now we have no choice, but we have to pair it up. So that becomes 2p4. Fluorine becomes 2p5. And then now finally, neon has a full shell. So I'm going to write that as full shell. 1s2, 2s2, 2p6, all that is filled. That's what makes it a noble gas. So as it turns out, having a full shell really stabilizes an atom. And now we can adopt a new nomenclature, right? So I can write 1s2, 2s2, 2p6 as just simply neon. So now once I go past neon, I could keep writing 1s2, 2s2, 2p6 and then keep going it. Or I could just abbreviate any 1s2, 2s2, 2p6 as just neon. And that becomes much easier to write. Okay? So now let's keep moving forward. Let's do sodium. So we know that sodium, right, we filled it up to neon. We know neon is 1s2, 2s2, 2p6. So let's do that. Here's my 1s2. Here's my 2s2. Here's my 2p6. 6, and notice I still put them in one at a time, okay? So all of that right there, sodium with 11 electrons, I could write as 1s2, 2s2, 2p6, or I could just simply write that as neon. But now I've got 11 electrons, right? That one extra electron is a 1, 2, 3s electron, right? That's the next level. So there it is, okay? So 1s2, 2s2, 2p6, 3s1, or just simply neon 3s1. Okay, so now I'm going to divert from filling out the rest of the atoms, and we're going to talk about a really interesting phenomenon. Why are group 1 elements always +1 when ionized? Right, so think back to this. We know that hydrogen, lithium, sodium, potassium, rubidium, cesium, francium, they're always +1 when ionized. Why? Well, let's do the electron configuration. So we know sodium solid is 11 electrons. But sodium plus has to have 10 electrons, right? When we make a cation out of it, we remove one single electron. So let's populate 10 electrons on this thing. It's going to go 1s2, 2s2. So there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay? So the electron configuration of sodium plus is the same as neon. We call this isoelectronic. Iso means the same. So sodium plus has the same electron configuration as neon, the noble gas. And if we were to do that example for potassium, okay, let's follow this. Potassium plus is the same as argon. Rubidium 1 plus is the same as krypton. Cesium 1 plus is the same as xenon, and so forth. So all of these elements are always +1 because that gives them the stable noble gas configuration. So sodium loves being sodium plus. And if I relate this to our discussion of potential energy, right? Go back to the thermodynamics. Sodium as a metal has a ton of potential energy to become sodium plus. It really, really wants to become sodium plus because it will have the stable electron configuration of neon. So sodium as a metal just has a ton of potential energy. So when sodium goes through this reaction where it releases an electron, that's very exothermic. And so if you've ever seen somebody throw a chunk of sodium into some water, it explodes and releases a ton of energy because sodium is having an electron released to give it that stable noble gas configuration. Okay? So the group 1 elements as solids just have an enormous amount of potential energy to become +1 ions. They really want to become +1 ions. That's why we observe them all as +1 ions in nature. All right? Whew, oh, excuse me. Okay, moving forward. So now what about the halogens? What about fluorine? Okay, so here's fluorine. So let's do its configuration. So it has 9 electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so that's 1s2, 2s2, 2p5. So now why are halogens always -1 when ionized? Well, look, now we've got 10 electrons, and maybe you can guess where this is going, right? There's fluoride, F-, and there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So also fluoride is isoelectronic with neon. And now if we notice here, right, look, fluoride becomes isoelectronic with neon. Chloride becomes isoelectronic with argon, bromide to krypton, iodide to xenon. So just like in the previous example, the halogens always are -1 because that gives them noble gas configuration. Well, what about oxygen? Why is oxygen always -2? Well, look, oxygen's always -2 because if it gains 1, 2 electrons, it also becomes isoelectronic with neon. Well, what about nitrogen? Why is nitrogen always -3? Once again, because 1, 2, 3, it becomes isoelectronic with neon. So all of those trends, all of those charges that I made you memorize back in the beginning, like why is aluminum always 3+? Well, aluminum's always 3+ because now when I go positive, I go backwards, right? So aluminum is always 3+ because now I go 1, 2, 3. Okay? Why is zinc always 2+? Well, this one gets complicated. We actually have to split over the D block, and I'll get to that in a moment. But zinc readily makes 2+ because we go back 2 spaces and we get to the noble gases. Okay? So that's pretty cool. All right?